they don't actually have physics on their test instead of that. So because of that, we're just going to do chemistry first. So if you guys can, pull out your chemistry Princeton review books. I found this is the best PowerPoint I could find online in terms of going over stoichiometry. But there's some things that are in the chapter that we're going to cover that aren't in this PowerPoint. So if you could, go ahead and flip to chapter 2. Okay, let me give you guys all microphone privileges. So if you do have questions, then you can unmute your microphones and ask them. There we go. Okay, so, all right, so could everyone unmute their microphones, please? Or sorry, mute them right now. Thank you for reminding me to record it. Perfect. Okay, so this meeting is now being recorded. All right, so the first concept in this chapter that I'm not a supporter of the Bulls, but I do like the heart that team plays with. But without Derrick Rose, they're not really going anywhere, and we all know that. And it's unfortunate that he keeps getting injured because he's such a good player. Hey, no, it's true. Okay, so the first thing that I want to go over is density. So density is pretty much a substance mass per volume. So, I mean, the definition is pretty much the formula as well. Density is represented by the Greek letter rho, which kind of looks like a P, and that equals mass over volume. So it's on page 18. I hope you guys have your books. So in terms of the MCAT, whenever they have problems for density, usually they're very, very simple density problems. And a lot of times they'll actually tie it into like other concepts like stoichiometry. They'll give you the density of something and you have to figure out how much of it is there and then go into a stoichiometry problem. But just the formula mass over volume will pretty much allow you to figure all that out. Usually what they'll do is they'll give you the volume of something and then they'll tell you the density of it. And based on that, you have to find the mass. So the example problem that they have in the book, they talk about diamonds, and they give you the density of 3,500 kilograms per meter squared, and they ask you what the volume is of a 1.34 or 1 3/4 carat diamond, where they give you how many grams a carat is, and based on that, it asks for the volume. So all you got to do is convert the number of carats into grams, and they tell you 1 carat equals 0.2 grams, and you would just use the formula density equals mass over volume to figure out the volume. So it's simple enough. For the MCAT, that's all you need to know about density, and in general, density is pretty simple. Now, that's one of the things that's not there in this PowerPoint, but let's go ahead and start looking at this PowerPoint. I think it's pretty good. It has a lot of examples, so hopefully it'll make all these concepts clear. And in general, this chapter is very, very basic and very easy, but at the same time, it's very important because there's a lot of stoichiometry problems on the MCAT. And if you master stoichiometry, if you just do a lot of practice problems of this stuff, you pretty much will be able to get a bunch of freebies on the MCAT. So make sure to understand everything and review it afterwards. Okay, so the mole. The mole is just a term for how many of something. And generally, it's talking about Avogadro's number, which is 6.02 times 23, or sorry, times 10 to the 23rd. And that's what a mole of something is. And it's a very unclear concept of what it is. But if you just know how to use it in terms of calculations, that's pretty much all you're going to need to know. Generally, when you're talking about moles, you have to think about the molecular weight of something. And the molecular weight of something is when you take whatever compound, let's just say H2O because it's simple. The molecular weight of H2O, you figure out how much does each hydrogen atom weigh and how much does the oxygen atom weigh, and you add them together. And that tells you how many grams per each mole that hydrogen or that H2O would be. So hydrogen is each mole is 1 gram. So there's 2 of those. That's 2. And oxygen, there's 16. So the molecular weight of H2O is 18. So if I told you that there's, let's say, 36 grams of H2O, somebody raise their hand and tell me how many moles that would be. Go ahead, Momin. You could either type it in the chat box or say it. Yeah, so it would be 2 moles because 1 mole would be 18 grams, so 36 grams would be 2 moles. It's as simple as that. And that's what the number actually looks like, but we always use it in scientific notation. So like I already said, the molecular weight, that's the weight in grams of a mole of a substance. So you'd be getting all this information from your periodic table, which is something that the MCAT provides. They always have, in the MCAT, in terms of the way the test is on the computer, in the corner there's a little box that says exhibit, and if you click on that, the periodic table pops up. And in general, for all of your molecular weights, you would just round to the nearest tenth, just to make it easier on you, because you don't get a calculator or anything. Plus, usually the answers are rounded anyway. And it doesn't depend, the molecular weight, it doesn't depend on amount, it's an intensive property. Okay, so try these molecular weights. So if you guys could pull up a periodic table either on your computer or pull it out of your book, what's the molecular weight of just calcium? Just the element calcium. You don't even have to raise your hand, just go ahead and type it. Yep, so it's pretty much 40 grams per mole. So the unit for that is grams per mole, because it's the amount of weight per mole, per 1 mole. What about diatomic hydrogen, just hydrogen gas? Yep. You do 2 times 1, which each hydrogen is 1, and it'd be 2. I don't know why it had that. It's pretty repetitive on the PowerPoint, but it seems like a lot of these PowerPoints are really repetitive. Okay, what about this one, barium fluoride? What's the molecular weight of barium fluoride? Yo, I'll teach you my class right here. Right away? My roommate just came in from work and he's about to go on a date, so. But everyone at work thinks that he's going to dinner with his dad, and that's why he pieced out of work early. That's funny. 175, let's see. Yep, so barium, it weighs 137.3, and then each fluoride is 19, so you just add those up and get 175. So what if you have 2 moles of barium fluoride? Then what do you have? It's pretty obvious. Wait a second. So, okay, I quoted. I said that. I kind of asked that question wrong. If you have 2 moles of barium fluoride, if it specifies 2 moles, what's the weight of that? Yes, it's 350. But if we're just talking about the molecular weight, that doesn't depend on the object. It's just per 1 mole every single time. Even if it's 50 BAF2, the molecular weight will still be the same. What would be different is the actual mass of that object. So sorry about that. Avogadro's number. This is a picture of Avogadro. It's very interesting. But Avogadro's number is 6.02 times 10 to the 23rd. But I'm sure through all of your schooling, you guys have all memorized that number. And it is something that you need to memorize for the MCAT if you haven't already. All right, so what is the molecular weight of carbon dioxide? Now, what is the weight of 3 moles? This time I'm not asking the molecular weight. How much does 3 moles of carbon dioxide weigh? Yeah. And the moles cancel out in terms of the year units, and that'd be 132 grams. So how much is it in grams per mole? So what is the molecular weight? Remember, it was the same as like that other one where it was 2 barium fluoride. It's the same thing, 44, because that's asking for the molecular weight. What's the molecular weight of nitrogen gas? This is kind of a trick question. Yep, you got it. So nitrogen gas is a diatomic molecule, so you have to think of it as N2. And so 2 nitrogens, if you add them up, it's 28 grams per mole. All right. Does anyone know which elements exist as diatomic molecules? Go ahead and add them in, or type them up in the chat box, the ones that you guys do know. There's a few of them, and you have to remember that these are diatomic for the MCAT, or else it'll trick you with questions. So there they are. So it is NHON and then the halogens. So you guys both got a bunch of them. Moment's got all of them. Okay, so let's look at this. All right, we have the formula AgNO3. First thing I want you guys to tell me is the molecular weight. What's the molecular weight of silver nitrate, I think? Go ahead and calculate it out.
Hey, moment.
I'll give you a second.
Moment.
Nobody? Alright, so the molecular weight is 169.9. Oh, shoot, okay. That's okay. Are you about to go pray as well? Because if you want, you can go. You go ahead and do that. And okay, so we'll just wait for you. I'll just chill out for a second and get this thing. Hey, once Danish gets back, we're ready to keep on going. Cool. Everybody is back. All right, so while you were gone, I kind of just revealed that the molecular weight of AgNO3 is 169.9 or 170. So, considering that considering that the mass that is just given to you in this situation is 15 grams, and the molecular weight is 170 grams per mole, how many moles do we have? How would you figure that out? Yep. So what would that give you in terms of the number? Pull out a calculator or something, or on your phone. Well, the grams is 15 grams. It's here in the PowerPoint. So you would just do 15 divided by 170, and that would give you the number of moles. .107. It would be 0.088 because you do 15 divided by 170. So now, given that, how would you figure out how many molecules there are? Exactly. So times Avogadro's number, and that gives you 5.3 times 10 to the 22nd. Oops. So from there, how do you figure out how many atoms there are? Wait, this is kind of a weird situation. I'm not exactly sure what they times the number of atoms. I think it's referring to something that wasn't mentioned on the slide, so just forget about that part. Here's a bunch more of just examples where you have, different gram amounts, and here are all the molecular weights. And the same way you would do that first one, you would divide it by the molecular weight of that particular molecule to get the moles, and you'd multiply that by Avogadro's number to get the molecules. Okay, now percent composition. Percent composition is pretty much determining, let me pull it up in the book so I can give you like a good definition. So, it doesn't really give a good definition in the book, but percent composition is when you take any molecule and you determine how much percent of that is each atom in terms of mass. So answer this question for me. In terms of NaCl, you got two atoms, right? Na and Cl. Does that mean that 50% of that mass is Na by weight or by mass? Exactly, so it's no. Because Na is 23 grams per mole and Cl is 35.5 grams per mole. So in order to do so, in order to find the percent composition by mass, what you would do is you would figure out the full molecular weight of that NaCl, and based on these molecular weights of each of those atoms, you would figure out what percentage of that atom is, what percentage by mass of that atom it is in that molecule. So in terms of sodium, to find percent of sodium, you would do the molecular weight of sodium over the molecular weight of the full compound, which is NaCl, and multiply it by 100. So since Na is 23 grams per mole, you would do 23 over, you'd find the total molecular weight of NaCl, so that would be 35.5, which is the molecular weight of the chlorine, and added to the 23, which is the sodium, and then you multiply that by 100, you get 39.3. So the percent sodium of that compound is 39.3%. Now, I want one of you guys to turn on your mics, and oh, John, you just joined us. Let me give you my privileges. Okay, so go ahead and mute that right now. Who wants to volunteer to find the percent oxygen in CaCO3? Tell me step by step, and then I'll show you the answer and let you know if you did it right. It was just like that last one. You would just do the molecular weight of that single element over molecular weight of the whole compound, and multiply by 100. So instead of typing it up, go ahead and say it, because I want you to go from by process, or by like explain the steps as you're doing it. Danish, I volunteer you because you started typing. Go ahead, unmute your mic and tell us how you did this problem. Okay. Well, somebody else go ahead and do it. Momin, I know your mic usually works, so why don't you try?
Ca is 40 grams per mole.
Mm-hmm.
Carbon is 12 grams per mole. And oxygen is 16 grams per mole.
Okay.
3 oxygens equals 48 over 40 plus 12 plus 48.
Yep.
Times 100% equals 48%.
All right. That's exactly how you do it. So, all right, go ahead and turn off your mic. Good job, Momin. So for that, it's 48% oxygen. And that's exactly how you do it. 3 times 16, because 16 is the amount of, well, there's 3 oxygens and each one is 16, and then the bottom is the molecular weight of the whole compound. And by doing that, you get the percent by mass. Now, John, you want to try this one? Or what about Ilsa? So remember, this one is asking how many grams of Mg is in 4 grams of MgO. So there's like one extra step after you get the percent composition. So go ahead and unmute your mic and try talking. Hopefully your mic is working.
Alright,
Okay, so it's going to be John. Ilsa, go ahead and mute your mic.
Oh, sorry. The molecular mass is 16 plus 24.3. So you divide 24.3 divided by 40.3 to get the percent of mg, and you multiply that by 4 grams to get 2.4 grams.
Yep, so you first calculate the mg by doing exactly what you said, 24 over the total. That gives you 60%. And then you just find 60% of the 4, which is 2.4. So, yep. You guys have a hang of the percent composition. So, in terms of, there's another thing that the MCAT might throw at you. They might even like have you compare an experimental value to an actual value, like a lab value. So you would figure out the experimental percentage, and then you have to figure out the accepted percentage, and then based on that you get your experimental error. So in this situation, you have this formula right here, Ag2O, and it breaks down into Ag plus 2O. So the first step that you have to do is you have to balance the formula. That's another thing that the MCAT does a lot of the times. They'll give you unbalanced formulas, and you have to go ahead and balance them. So it's kind of annoying because there's no need for them to do that. But all the time, it's almost like a trick question. You have to realize that the formula that they gave you is obviously unbalanced. Like when you see this formula, you automatically know it's unbalanced because there's 2 Ags on one side, only 1 on the other. There's 1 O on one side and 2 on the other. So in order to balance it, you would have to put a coefficient of 2 in front of the Ag2O2 and make it 4Ag. So that balances the formula. That's the first step. Yep, perfect. Yeah, I didn't even ask you, but yeah, that's right. So the given information told us that 4 grams of the reactant creates 3.65 grams of the Ag on the product side. So in order to figure out the experimental percent of Ag, you do simply just the total, the amount of the first one over the amount of the total molecular weight of the Ag, or the amount that they give you in terms of the reactant, sorry. And that gives you about 91.3%. And the true value, you're actually, so this value over here is the experimental value. So based on our experiment, we got the percent composition being 91.3. But the true value, you'd be looking at the molecular weights. And if you do that, you end up getting about 93.1. So it's a little bit off because, whenever you have an experimental value, it's always going to be a little bit off of the actual value. And in the MCAT, they might ask you, what was the percent error of that experiment? And the formula for that is you would find the difference between the experimental value and the accepted value, and you do it over, you would divide that by the accepted value and then times 100 to get the percent. So in this situation, it's 91.3 minus 93.1 divided by 93.1 times 100, and that gives you about 1.9% error. And usually, they actually, here it has it in negative, but normally it's done in absolute value, so it would be 1.9%, even if it was 1.9% more. Alright, so the next topic I want to talk about is an empirical formula. An empirical formula is the simplest formula indicating the mole ratio of elements in a compound. So, for example, if you have H2O2, if you simplified that, since there's 2 of each, it would just be HO. Now, C6H6, again, is just CH because there's 6 of each. What about N2O4? Somebody type in the chat box, what is the empirical formula of N2O4? Yep. NO2, correct. Now, what about CO2? What's the empirical formula of CO2? Yep, so what if I gave you C2H6, Here, I'll type it in the chat box. C2H6O10. So now, what is the empirical formula of that one I just typed there? Yep, there you go. CH3O5. All right, so in terms of the steps for an empirical formula question, they'll usually they'll give you something in grams. You would convert that to moles, and you would divide by the least number of moles for the ratio, and then apply the ratio to the formula. I know if you just look at these steps, it's kind of confusing, but let's do an example problem, and that'll help a little bit. So the example says the compound contains 0.9 grams of calcium and 1.6 grams of chlorine. So to figure out what the actual molecular formula of this is, or empirical formula, let's see. So the first thing you would do is you would take the grams and you'd convert it to the number of moles. So in terms of 0.9 grams of calcium, it converts to 0.022 moles of calcium. And the other one, the 1.6 grams of chlorine, it converts to 0.045 moles of chlorine. Now, you would divide them, and you'd figure out that there's 2 chlorines to every calcium. So what you do is you take the larger value of moles, and you divide it by the smaller value of the moles. And that will give you how many of one to the other. So here it gives you 2. So that tells you that there's 2 chlorines to every calcium. So you know that the formula is going to be CaCl2. Now let's do another one. So 0.556 grams of carbon and 0.0933 grams of hydrogen. Ilsa, you can do this one because you didn't do the last one. Go ahead and unmute your mic and tell me your steps.
What are we supposed to be doing for this one?
You're supposed to be, based on these numbers I gave you, I want you to figure out what the empirical formula of this molecule is. Kind of like in the last one, so if you look at the last one, these were the steps. So we figured out the number of moles, and we divided the larger amount of moles by the smaller amount of moles, and then we were able to figure out our empirical formula. So just like that, I want you to do it for carbon and hydrogen, for these 2 amounts.
Okay. So first we need to find the moles of both.
Mm-hmm.
So let's see. Well, do you want to just do this one? I'm kind of confused.
Yeah, sure, I can do it, this one. So first thing is we have carbon. So carbon is 12 grams per mole, right? So you would divide the 0.556 grams of carbon by the 12, and you get the amount of moles of the carbon in this compound. Now you do the same thing with hydrogen, and you know that hydrogen is just 1. So you have 0.0933 moles of hydrogen. So now we have the molar amounts of both elements in the compound. So you would divide the larger value by the smaller one. So here we have more moles of hydrogen than carbon. So what you would do is 0.0933 moles. The molar amount of the hydrogen divided by the molar amount of the carbon. And that tells you that there's going to be, since that equals 2, that tells you there's going to be 2 hydrogens for every carbon. So that kind of gives you the molar ratio. And based on that, your empirical formula, you know that it's going to be CH2. Oh, that's just a typo. I think it's supposed to be 0.556. I'd have to check with my calculator, but I think that's just a typo. Okay, so why is the empirical formula a ratio of small whole numbers? It's always whole numbers because you can't have half of an atom, and also atoms combine as whole units, and it shows that it's the simplest way that the atoms compare. So pretty much it's telling you the molar ratio of these atoms within the molecular formula. Now, what formula would this ratio give? Who wants to take on this one? We've done 2 of them already, so it's the same process. Except this time you have 3 of them. But based on that, you can, So it's KNO3. You know that because you know that there's going to be 3 of the, for each one of the K and the N, there's going to be 3 oxygens because you know that there's approximately 0.75 moles of that, and there's only 0.25 of the other ones. So that tells you that there's going to be 3 oxygens for every one of the other 2. So it's KNO3. Okay, so now I'm going to give you the percent composition, and I want you to tell me the moles. So, I'll just walk you guys through this problem. So, if you have 70.5% Fe and 29.5% oxygen, well, the first step you would do on something like this, you would assume that there's 100 grams of that substance, just because it makes it easier to work with those values, and you can figure out how many moles there are just from that. So, you would take, if there's 100 grams of that substance, if 70.5% of it is iron, that means 70.5 grams of it would be iron, just based on that percentage. So you divide that by the molecular weight, which is of iron, which is 55.9. That tells you the amount of moles of iron. You do the same thing with oxygen. That tells you the amount of moles of oxygen. And as simple as that. So based off that, you can figure out the empirical formula. If you divide the 1.84 divided by 1.26, you find out that you need 1.5 of oxygen for every iron. But this is not an empirical formula because, like we said in that other slide, it has to be whole numbers. So you would multiply this by 2, and you got your empirical formula, which is Fe2O3. Now, who wants to give this one a try? Same process, but with 3. John, you want to try it? I think there might be a little bit of lag on here. Momin, you want to give it a try? Okay, John's got it. Okay, so you've got H2O. So we got 3.3 moles of carbon. We go step by step. And then we got, by the same process, we have 6.7 moles of hydrogen and 3.3 moles of oxygen. So, exactly. So CH2O. Why doesn't the ratio of the percentage give the empirical formula? So you have to account for the differing masses of the elements. That's why you can't just take the percentages that they give you at the very top of that slide and just come up with the molecular formula. You have to take into account the masses. And that kind of just, it I guess, integrates the concept of like the percent composition by mass as well. Why did the ratio of the moles give the empirical formula? Because the ratio of the number of atoms normalizes for the mass differences. Okay, so molecular formulas. The molecular formulas are the formula of the actual compound as it exists in molecules. And that tells you the actual number of each element in that formula. So benzene, it exists as, even though the molecular formula for it would be CH, it actually exists as C6H6. Hydrogen peroxide exists as H2O2, not HO. This is the actual compound. Okay, so in this situation, we have the empirical formula of HO, but they give us that the molecular weight of the actual compound is 34 grams per mole. So what you would figure out is what the molecular weight of the empirical formula is. So the empirical formula is just an H and an O. So that would be 17. So if you multiply 17 by 2, you get 34. So you have to multiply the HO by 2, and you get H2O2. And that's how you figure out a molecular formula if they just give you 2 of these 4 things. Another example, you have CHOCl2. So that's the empirical formula, and the molecular weight is 200 grams per mole. So somebody chime in and tell me what the molecular weight of the empirical formula is. So add up the amounts for the empirical formula that's given. And just type it in the chat box. Yep, that's 100. So what does that make our molecular formula? Anybody? Yep, that's right. So C2H2O2Cl4. That's right, John. All right, one more example of this stuff. Gave you a molecular formula, gave you an empirical formula. Somebody tell me the molecular weight and the molecular formula. That's CCl, not CCI. So carbon, chlorine, and 2 nitrogens. Yep, 75.5. So what does that make our molecular formula? Exactly. Cool. Why is the molecular weight needed to determine the molecular formula? Because you need the molecular weight of the actual compound to figure out how many of each atoms there is in the molecule. Because all the empirical formula tells you is the molar ratio, not the actual number of each one. Now we got to do a little bit of stoichiometry, and then after stoichiometry, we'll be done. So stoichiometry is pretty much converting. You'll have a reaction, which first step is balancing. Like I said, it takes a little practice, but once you get a hang of it, it's not hard at all. And then they're going to give you generally an amount of either a reactant or a product in grams, and they want you to either go forward and figure out how many grams of if they give you the reactant in grams, they're going to go and ask you how many grams are there of a product, and you have to figure that out through stoichiometry. Or if they give you the amount of a product, they'll be like, how many grams of the reactant was needed in order to get this much product? And again, you have to go through stoichiometry to do that. And the definition of stoichiometry is it's just a method of problem solving that's involving mass-to-mass relationships in chemical changes, so in chemical reactions. Yep, that's exactly the process. So, how many grams of rust are formed when 12 grams of iron reacts with oxygen? So, you have to use balanced equations to get the correct molar ratios. So, okay, so that doesn't actually answer our question, our example back there. Here's our balanced equation for that example problem. You have 4 iron molecules plus 3 oxygen, like diatomic oxygen gas particles, yield 2 Fe2O3, which is the rust. So the molar ratios is 4 to 3 to 2. So for every 4 moles of iron that's reacted, you get 2 moles of the rust. Or for every 3 moles of the oxygen, you get 2 moles of the rust. So this is what I just said. 2 moles of rust will form. 8 moles of iron rust and 4 moles of the 4 moles of the Fe2O3 will form. So whatever Moment said is right. So the first thing is you have to determine the molar ratio from the equation by just looking at the numbers, the coefficients. Then whatever gram amount that they give you, you have to convert that to moles. Then you apply the molar ratio, and then you convert the moles to grams. So back in this problem, let's clear up this board a little bit, and let me see if I can draw it. There we go. Okay, so just as an example, if they say that there's, this is hard to do, I wish I had a little mouse. If there's 10 grams of iron, and they ask, if there's 10 grams, how many, this is the question mark right here, how many grams of Fe2O3 is formed? The process that you would first do is, first you got to convert this 10 grams into moles. So I'm not actually going to put the values here because I just chose random numbers. I don't know if they'll actually end up being pretty numbers if we use the actual values for the molecular weights. But you would do 10 grams. Wow, this is really hard to draw on here without a mouse. Okay, so 10 grams of Fe. You know what? Give me a second. I'm going to go grab a mouse from upstairs. Be right back. Alright, let's see if this works, if I can just plug it. Nope, not working. Alright, we're just going to try this. So I'll just do this one example problem, and then I won't draw on this thing anymore unless I get a mouse that works. So you'd multiply that. So whenever you do dimensional analysis, you want to have, since we have grams on top to start, you want grams on the bottom. So you'd find the molecular weight of that, which would be, I don't know what it is, but we'll just write MW grams I really need to get that whiteboard from Dr. Sutton. I think that'll help a lot for something like this. Of Fe. Would be one of that many grams would be 1 mole. There we go. Of Fe. So if you do this, these two will cancel out right here. The grams of Fe here and the grams of Fe here. So now we're going to know how many moles of Fe are there. Now the next step, you'd multiply that by the molar ratio. So you know that in this situation, you'd have 4 moles of Fe on the bottom because you want to cancel out that moles of Fe. And then that would yield 2 moles of the product. So I'm actually not going to keep drawing this because this is really annoying. And that'll cancel out moles of Fe. So now we'll have our answer in terms of the moles of the product. And then all you got to do after that is you have to apply the molecular weight of that product. You would have moles on the bottom of that product, which would cancel out the moles up here. So you cancel this part out. And if you had your final step, you cancel out the moles of the product at the bottom. And this top part right here would just be the molecular weight in grams. So molecular weight. And your final answer, you'd be able to figure out how many grams of the product. So that's kind of how you do a dimensional analysis problem. Drawing on here was super annoying, so we're not going to do that again. Let's go to the next slide. Oh, great. I didn't even realize the slide was right there, where it would have set it all up for us. So in this example, there's 28 grams of Fe. It's asking how many grams of the product there would be. So first you want to figure out how many moles there are using the molecular mass. So you're converting it into moles, the grams to moles. Then you're using the ratio. So 2 to 1. I use 4 to 2, but 2 to 1 is the same thing. And you would find out that there's 0.25 moles of the product. And then the next thing is you have to convert that to grams. So you'd use the molecular mass again and multiply it this time. You figure out that there's 40 grams of your product. I think we're almost done, guys. Oh, are we actually done? Cool. Perfect. We're done with all that stuff. We finished it in an hour, which is awesome. Does anyone have any questions on stoichiometry? So the next chapter is atomic structure, and the atomic structure. I want to see if I can. Okay, let me stop sharing this PowerPoint. Let me see if it's possible for me to throw on a. So okay, let's talk about the very basics first, because the very basics are stuff that you guys already know. In terms of, what an atom is. You know that an atom it has a nucleus and an electron cloud. And in the nucleus, you have protons and neutrons. Protons have a positive charge. Neutrons have a neutral charge. Electrons obviously have a negative charge. And protons and neutrons are about equal size, and electrons are much smaller. So that's the basic stuff. Now, you have a few different things in terms of the periodic table. You have the atomic number, which that's the one that determines what element an atom is. That's the number of protons, and it's represented by Z. Sorry if I'm going fast, but I think this is stuff that you guys all already know. So Z is the atomic number, and that's the number of protons, and that's the actual number in the atom or in the periodic table. Now, the mass number is A, and that's going to give you the number of protons plus the number of neutrons. So A equals Z, which is the atomic number, plus N, which is the number of neutrons. Isotopes are the same whenever you have the same element, but they differ in the number of neutrons. So that's just the definition of isotope. So whenever you have like carbon-14, that's just normally carbon has, it's carbon-12. Carbon-14 would be considered an isotope of carbon because it has 2 extra neutrons. But everything else about it is the same. Whenever you have ions, that means that your atom has either gained or lost electrons, and as a result, it now has a charge. It either has a positive charge or a negative charge, and those are called ions. So whenever an ion is positively charged, it's called a cation, C-A-T-I-O-N. Whenever it's negatively charged, it's anion, A-N-I-O-N. Now, this is the part. Now we're going to discuss electron quantum numbers real quick. And I want to see if I can pull up a YouTube video and show it on here, because I think it does a good job explaining it. Let me pull it up first, and then I'll try and share my screen, and hopefully it works. Give me 1 second. All right, hold on 1 second. It's just loading. I'm not exactly sure if this is going to work, but we'll see. Oh, Adobe Connect add-in is incompatible with the default settings of my version of Google Chrome. Well, let me just put the link of this. Let me just copy paste the link of this into the chat box. And okay, the connection's not necessarily low. I think it's just when I'm running Adobe Connect and trying to use the internet at the same time, it's not working very well. So in terms of the quantum numbers, I want you guys to watch that video because quantum numbers are, I mean, first of all, they're not super important for the MCAT, but it's something that you do need to know. And I think this video does a very good job explaining quantum numbers. And that actually pretty much, the second part of this chapter, I was actually going to cover at the very end because I think it's more helpful to talk about the way that decay happens and the way that your emission and atomic spectra works after we do some of the later chapters of chemistry. So this link, go ahead and open it up before I end out of the session. But does anyone have, I know that the second chapter we didn't cover in very much detail yet, but it's because half of that chapter I want to cover it later after we cover some other material. Does anyone have any questions so far? Or of anything that we covered today? Yeah, so we are working on chemistry. And the reason in that is because I want to keep you guys on the same schedule as my other class. And in my other class, I have DAT students and PCAT students, and they don't have physics as a part of their test. So what they have to do is, when we do physics, they actually switch out. Yeah, we do really need a whiteboard because that drawing was a pain in the ass. But they have to do math during when we do physics, and I don't think that part is set up yet in terms of having the teacher ready and everything. So so we're gonna do chemistry first. Chemistry, we're gonna be done with it in a couple weeks, and then we'll do. If the math stuff is already set up, then we'll do physics. If not, we're gonna do organic chemistry. I'm actually not sure if organic chemistry is on their test either. So I really just got to talk to Dr. Sutton about that and figure it all out. Yeah, for the MCAT, what's the question? Yeah. Well, their test has a whole nother animal. There's this thing called like some sort of like perceptive something where it's a bunch of like weird like spatial problems. Is it really necessary to read the MCAT book because we know how to calculate all the general stuff? It's still. I think you should still read the book. You should still read the book just to make sure, because you don't want there to be something that you forgot that that's in there. So I mean, at least skim through it. Do practice problems. Obviously, one way you're going to figure out if there's concepts that you do need to cover in more detail is through practice passages. So on that Google Drive that I uploaded a bunch of the Berkeley Review passages. So are we going to have more equations problems or definition concepts? Honestly, it's a little bit of both. I think the Berkeley Review passages are really good for this stuff because they actually combine a lot of the conceptual stuff with the actual application of the equations. So in terms of the actual MCAT, honestly, it's mostly conceptual, but there is a little bit of math. But if you know how to use concepts to do the math, such as the Berkeley Review passages, then you're going to have no problem with the MCAT at all. In terms of problems, I would recommend Berkeley. I like exam crackers also because those are like good in terms of reinforcing material, but I wouldn't do just exam crackers. I would do exam crackers and Berkeley. And if you guys have heard of the company that I personally use, it's called Gold Standard, and on their website, I think it's mcatprep.com or something like that. Let me see, .com. Barron's, I don't really know much about Barron's. I haven't really used Barron's. But mcatprep.com, or maybe it's org. I think it's com. But on there, that's the Gold Standard MCAT website. They have practice tests. There's, I think, 10 of them. It's only $150, so it's not too expensive. Those are really good, too. Those are, I would say, on the same level as Berkeley, if not better. They're really, really hard practice tests. So what I did is, since I studied with those, like the AMCs were kind of a breeze. I was scoring at first, right around 30 on the Gold Standard test. Eventually, by the time I finished the 10th one, I was up to 33, 34. And then when I was taking the AMCs, I was pretty much dominating them. And because of that, I think I did well on the MCAT. So Gold Standard MCAT practice test, I would definitely recommend. Can you read exam crackers into the Princeton Review? I'm more familiar with the 1001 exam cracker books, not the actual content review. If you don't like Princeton Review, don't use it. Use something else then, because I agree with you. There's some concepts in the Princeton Review where it almost confuses you more than helps. So really, the point is you want to understand the content. So all of the books will cover the same content, just explain it differently. So if you don't like the Princeton Review, don't use it. You don't want it to end up hurting you more than helping you. So, all right. So one more thing I wanted to say: tomorrow's class, we're not gonna have class tomorrow. Kaplan has way too many details. I used Kaplan for my first 2 tests, and they make you memorize and learn stuff that is not even relevant on the MCAT. So that's how I feel about Kaplan. I think the Kaplan practice tests are horrible also. So that's just my opinion. But I mean, then again, I know people that have done well doing Kaplan, but it really just is going to depend on you. Me personally, I didn't like Kaplan. So tomorrow we're not going to have a class at regular time on Thursday. So in fact, our Thursday class, I'm going to New Orleans this weekend. Tomorrow I'm driving to New Orleans. So whatever the content that we were going to review on Thursday, I'm actually going to hold the online class on Saturday at 11 here. Saturday 11 p.m. to 1 p.m. And that one it's going to be combining both this class and the other class as well. Oh, sorry, not p.m. 11 a.m. to 1 p.m. on Saturday. I was actually going to get Dr. Sutton to teach tomorrow's class, but I haven't been able to get in contact with him because I think I said it the other day, but he just had a grandchild, so I think he's probably pretty busy with that. So plus on Saturday, if he wanted to teach that, he actually has his radio show on Saturday. So I'm just going to teach this class from New Orleans on Saturday at 11 o'clock. So just make sure y'all know. I'll send a reminder email just in case. Yep, Saturday. 11 in the morning. I'm going to stop the recording because we've already gone over the material. Okay, so recording is stopped. Saturday, 11 o'clock. No class tomorrow on Thursday. Hopefully, I will be functional Saturday at 11 o'clock because I'm going to be in New Orleans for Mardi Gras, but I'm confident that I'll be fine. I had to make sure to stop the recording before I said that part. But don't worry, I won't go too crazy on Friday night because I know I have to teach class on Saturday. Thanks. Don't take off my shirt. I'll try not to. I'll keep that in mind, Moment. I'll let others do it for me. The fine ladies in New Orleans, hopefully. Alright guys, I'm going to go ahead and end the meeting. Class is good. See you guys on Saturday.